Hello. Today we're going to start talking about sampled signals. We've been using them. We've been using X of n and related signals and many things, and now it's time to talk about where they come from and what we can do with them. So this is a picture we showed at the beginning of this course. We have an analog signal and we convert it to a digital signal essentially by quantizing the level as shown in the lower path and by quantizing the times at which we can view that signal, and we view that in the upper path. Combining those two gives us a digital signal. In this section we're going to talk about both aspects of this, both quantizing the levels and sampling in time, but we'll start by looking at just the sampling process as shown up here. So this will be ideal, and the idea is that we have a continuous time signal which, although using our notation, the parentheses with the t should indicate that. I'm going to put a c by it just in case, or just to make it extra clear. And if I were working on a computer system, I would mention that this next part is my analog to digital converter, or ADC. But right now we're just doing the ideal sampling, so we're going to call it a continuous to discrete converter, or a C to D. And what we get out is xn is equal to xc evaluated at the points where t is equal to n, which is an integer, times the sampling period. So this is periodic sampling, meaning that the samples are all evenly spaced. So as we did with our other things, we're going to start by looking at some relatively simple signals. And so let's start with a sinusoid, and it'll become clear later. We'll say x1 of t is equal to a cosine omega naught, and we'll use capital omega here, which is following the notation of the text for continuous time signals. Then when we sample it using our C to D converter, we get A, because it doesn't affect that, omega naught, and now where we had a t, we now do n cap t plus phi, and we can write this as A cosine little omega naught n plus phi by making the substitution omega naught is equal to, oops, no n in there, capital omega naught times t. It's very important. I'd normally box it in red, but it's already red, so I'll box it in green. Okay, so we've sampled our sinusoid. Now let's explore what can go wrong and where we might have possible issues. Let's do another one. We'll call it x2 of t, and it is essentially the same function, except that now we have omega naught plus 2 pi over t times t plus phi. So when we sample that, we get x2, so I should put the x1 up there. x2 of n is going to be a cosine, and now we get omega naught plus 2 pi over t all times n cap t plus phi. And you might guess that I chose this for a reason. I didn't just pull it out of a hat, and you would be correct. We have capital omega naught times nt, and we can combine the omega naught and the t to give us a little omega naught times n. And then we have 2 pi over t times nt, so we're going to have plus 2 pi n. And then, of course, the phase is not impacted. Well, we know that anytime you add 2 pi to the argument of a cosine, since it's periodic with a period of 2 pi, you get the original signal back. So this is just equal to omega naught n plus phi. Cosine is periodic. Okay. So this is a little bit troubling. We have two different signals that we started out with. X1 and X2 are different, and the sampled versions are identical. So that's what we call aliasing. Okay, well, if that wasn't bad enough, let's look at another example. In this one, let's start with x3 of t is equal to a cosine, put the big square bracket here because we'll have several things in here. This will be 2 pi over t minus omega naught times t plus phi. And now our sampled version, x3n, is going to come out to be a cosine. That all works out the same. We're going to get now a 2 pi over t minus omega naught times n cap t plus phi, which will be simply a cosine of 2 pi n minus omega naught n plus phi. Once again, our 2 pi factor can be taken out because we have a periodic cosine. So this is going to be a cosine of negative omega naught n plus phi. Well, good. At least this is different from our previous one. But it does have the same frequency. It didn't start with the same frequency. It ended with the same frequency. But we have this troubling negative sign out here. Remember that cosine is an even function. And an even function is one in which I'll use something different. G of x is equal to g of minus x. I could have put a t or an n or whatever else we have in there. But we can do the same thing here. So this is just equal to, do that in blue, a cosine negative omega naught minus phi. So we call this folding, and in the previous course, 2026, that we offer at Georgia Tech on this, there's a distinction made between folding and aliasing, and sometimes people forget that yes, it is different in that we now have a negative phase where we started with a positive phase, but in general, folding is just another type of aliasing. Why is that? Well, when we talk about aliasing, what we really are concerned with is what happens to the frequency. The phase may be flipped or may be retained, but as long as signals of different frequency end up at the same frequency, that's a problem. If we were to take the Fourier transform of the DTFT of, say, x2 plus x3, they would show up at the same frequency, and their phases would be different, and there would be no way to disentangle those anymore. What we would get would be a single frequency term with some phase related to the original phases of the two. And so because of this, whatever type of aliasing it is, it's a problem. So let's see what we can do about this problem of aliasing. As we'll learn soon, the ideal discrete to continuous converter, that's the one that goes the other way around from samples to a continuous time signal, takes the samples and reconstructs the lowest frequency alias. I guess this is new terms. Let's put discrete to continuous. So, for example, let's say we had several samples like this. The distance between these is t in time. And when we reconstruct this signal, we would have multiple sine waves that would fit this. That one. That one. And so on and so forth. You can imagine any number that might go there. So, when we sample a signal, we want to be able to reconstruct the original signal. So we must constrain our sampling period in such a way as to make this happen. This constraint on our sampling period is called the Nyquist criteria, and essentially it says that 2 pi over t must be greater than 2 times, now we've used capital omega naught, and now I'm going to use capital omega max, because if you have multiple signals, multiple sinusoids added together, then we have to find the largest frequency and say that our sampling period must be such that 2 pi over t is greater than 2 omega naught. So what is 2 pi over t? Just recall that 2 pi, well actually let's just start here. 1 over t, 1 over period is equal to frequency. So 2 pi over t is equal to some omega term, right? It's a frequency in radians per second. And in this particular case, we often put an S down there to indicate that it's our sample frequency, or the frequency with which we were taking samples, either in Hertz or in radians per second. Okay, another thing to note is that we must be at greater than twice the highest frequency. So I'll just draw a quick little example here and show kind of why that is. You pretend that's a perfect sinusoid, and this will be a lot more pleasant for everybody. So what this is saying is we have to take samples at least or greater than twice per period. So for example, if I took one sample here, next one would need to be here, and so on and so forth. And with this, there is no lower frequency signal that could be reproduced to go through all of those samples. So this would be the lowest frequency alias, and our reconstruction could be perfect. Note, if on the other hand we had exactly 2 samples per period, we might run into a problem. Just to illustrate this problem, here is a set of samples that are 2 samples per period. In green there, and those ones would obviously not be useful in recreating the original signal because it would all be zeros. So we have to have greater than twice the highest frequency needs to be our sample frequency. We often illustrate this graphically, and we're going to see these triangle plots all the time, because it's just a nice way to visualize what's going on. And so in this case, we're looking at frequency on the x-axis. So our continuous time frequency, 0 is there. And it's usually symmetric, in as much as this might be symmetric. It's kind of hard to tell with my artistic abilities. This would be the frequency spectrum of a continuous time signal. And if this were the frequency spectrum of a sinusoid, we would just have 2 impulses, showing that it existed only at one frequency and at that frequency's negative, at the negative of that frequency. But in general, a signal will have many frequencies present in it, and that's why not everything sounds like a pure tone. And so this signal, pardon me, or this point would be theta max, and this would be, or omega max, and this would be minus omega max right at that point. So next time we're going to go back and talk about how we might actually do this ideal reconstruction, and then bring this all together, I hope, in a better picture of what's going on with sampling and reconstruction.